This is chapter 8. It deals with memory management. We are going to look at various aspects of the management of memory in computers. We will look at swapping, contiguous memory allocation, paging, structure of the page table, segmentation, and finally, we will look briefly at the Intel Pentium as an example of memory management technique. This tutorial provides a detailed description of various ways of organizing memory hardware. You know that in a computer there is more than one memory location and there is more than one type of memory. How do you organize this memory? We are going to focus on the main memory, of course, which is referred to as the RAM. And then we will look at the techniques used in the management of memory, including paging techniques and segmentation techniques. And as I said earlier, finally, we will look at the Intel Pentium that supports both techniques, the segment and the segmentation with paging. When a program is run, it is brought from the storage, which is usually a hard disk or equivalent, into the memory, into the RAM, and it gets transformed as a process in order to be run. Now, here, not all the program needs to be taken from the storage to the main memory. We only need to take the parts of the program that are going to be processed. The main memory and the registers are the only storage areas that the CPU can access directly. The CPU can access by sending it instructions so that the main memory can send back data or instructions to the CPU. In addition to that, of course, the registers are accessed directly for temporary storage of data. The access to a register happens in one CPU clock cycle, or it might take less than that time. Whereas the access to an item in the main memory can take many cycles. The cache, which is also a relatively small memory, sits between the main memory and the CPU registers. And the memory contents have to be protected in order to ensure proper operation. Protected in many ways, as we will see in the next few slides. The base and limit registers. These are registers that contain the base and the limit that define the logical address space. If you look at this diagram depicting a portion of the main memory, this diagram shows a portion of the main memory containing the operating system, as well as some of the processes that have been brought in from the storage medium to be processed by the CPU, and therefore they have to be brought in as a first in the main memory. And you can see on the left a list of addresses showing the starting and the ending address of each process. Now, because there are so many things stored in the main memory, the starting address of a certain process has to be defined somewhere. And in this case, it is defined as the content of what is called the base register. The base register contains the start of a process. What about the length of the process? Again, starting with the value of the address in the base register, we consider that the length of the process has to be stored in another register called the limit register. So these two registers, the base defining the start and the limit defining the length of the process, these two registers define our process that is stored in the main memory ready for execution. Now, there has to be a process of binding the instructions and the data to the memory addresses that exist in the main. The instructions and the data included in a certain process to the memory addresses happens in three different stages. The first stage is during the compile time. If the memory is known beforehand, generated, and we must recompile the code if the starting location changes within the main memory. So anytime that the starting location of a certain process changes, then the absolute code of the program can or has to be recompiled. The second stage of binding happens at load time. If the memory location in the main memory is not known at the compile time, then we must generate a relocatable code. And then we have the of bindings at the execution time. In this case, the binding does not happen and it is delayed until the runtime. If the process is moved or can be moved during execution from one memory segment to another. In that case, it is preferred not to bind it until execution time. Again, in many designs, you will need the hardware to support the mapping of addresses. For example, you might need base and limit registers program. You have the source program of your program. This will produce what is called an object module. There are other objects this at this stage. This in the processing of a program. Now, in order to properly manage the memory, we have to binding of address space to a physical of the logical address, virtual address is referred to as logical virtual address. And when we talk about the physical address, this is the actual address as seen by the memory itself. These two types of addresses are the same in the compile time state in the load time state. They differ in the execution time management unit, MMU for short, is the hardware address and the mapping between the virtual or logical address to the physical address happens at the memory management unit. The value in the relocation register in memory, you have the logical address coming from the CPU. And in this example, let us assume that it is address 346. In the memory management unit, you have a relocation register. Again, in this example, it is 14000, and this has to be added to the logical address that has been generated by the CPU in order to produce the physical address of the main memory. So the 14000 is added to the 346 to produce 14346, which is the actual physical address that exists in the main memory. And as I said, this happens through the memory management unit. Now, the issue of dynamic loading. In this case, we do not load a routine until it is called. So during the program code, when a certain routine is called, then it is loaded. Better utilization of the memory space, so that if a routine is unused, there is no need to load it. And the time at which we load the routine is only when it is called. In certain cases, you will find the benefit of such an approach. For example, if you have large amounts of code that handle infrequently occurring cases, so you have a small amount of cases that do not happen frequently. However, handling these cases requires a large amount of code. Then there is no point in loading the routine fully, because first you are going to use it infrequently, and second, you might as well use the large space required for that for other purposes in the memory. Now, the support from the operating system is not required in such a case. The arrangement of this procedure happens through the design of your program. What about dynamic linking? The linking is delayed until the execution time. There is a term called stub, and this refers to a small piece of code used for a certain purpose. The stub is used to locate the appropriate memory resident library routine. The stub replaces itself with the address of the routine and executes the routine. So instead of dealing with the resident library routine, you deal with the stub instead. And the stub locates the routine that you are dealing with. So it is a representation of the routine. Once you use a stub, then this stub is replaced with the address of the routine, and then the routine will be executed. However, in this case, you need the operating system to check whether the routine is in the process's memory address or not. Because to do this operation, the routine has to be in the process's memory address. The dynamic linking is useful for libraries. And this process is sometimes referred to as shared libraries process. Now, when you have limited amount of space in the main memory, you can do another procedure called swapping. This involves swapping out of memory to a backing store, or swapping back from the backing store into the memory of a process. So if a process does not need to be run immediately, then its space in the main memory can be used for other processes, and it can be swapped temporarily out of the memory until the time comes when it is really needed to be run. The backing store is a fast disk that is very large, and it stores copies of all memory images for all users. This backing store provides direct access to these memory images for the users. Another operation that could be involved is the roll out and the roll in. This is the operation of swapping used for priority-based scheduling algorithms. Lower priority process is swapped out to make room for higher priority process. In this case, the higher priority process is loaded into the main memory. It gets executed, and when it is completed, then the low priority process can be brought in, and it will take in turn its execution. Let us define a term called hole, which is a block of available memory. Now, when you keep dynamically changing the locations of the various processes, they would occupy various areas in the main memory. And because the areas occupied by these various processes differ, then there could be holes of various sizes scattered throughout the main memory, resulting from this continuous movement of the processes. For example, if you have a large process that is completed, swapped out into the storage medium, then its area could be larger than the needed area for another process. What happens to the difference between the areas of the old swapped out process and the incoming new process? It will form a hole. Conversely, when a process is incoming, when it arrives to the main memory, it is allocated memory from a hole large enough to accommodate it. It cannot be allocated a hole that has a smaller area than it would require. The hole must be larger than the area required by the new incoming process. Therefore, there has to be a certain type of information that is kept by the operating system, and this is referred to in the allocation of processes in holes. This information contains information about allocated partitions and about the holes, which are the remaining free partitions. In the diagram, you will see the main memory with the operating system occupying a part of it, and then you have on the left three processes: process 2, process 8, and process 5. You can see that these three processes are not of equal size. When process 8 gets completed and is swapped out, it leaves a hole in its place. If there is another process, 9, that needs to be brought in or swapped in to the main memory for execution, then process 9 is brought in to a part of the large hole. This also leaves a vacant part in the main memory. Another process, 10, in this example, could be swapped in to the main memory, and this will be allocated a certain portion of the remaining hole, and so on until the remaining size of the hole does not accommodate any new incoming process. Now, this brings in a dynamic storage allocation. The question here is how to satisfy a request of size n from a list of free holes. There are a few algorithms that can be followed to satisfy this request. The first involves a first fit algorithm. In the first fit algorithm, we allocate a hole that is big enough to accommodate the required process. So you go through the main memory, and the first hole that is big enough to accommodate the process, the first hole that is large enough so that the new incoming process can be fitted in it, will be selected. The second algorithm is fit algorithm. In this case, we allocate the smallest hole that is big enough. The idea here is that you allocate the hole that is big enough to accommodate the incoming process, but that at the same time does not leave a lot of empty space so that it will fit in the best possible way the new incoming process. To be able to perform this algorithm, then the entire list of holes has to be searched so that you can identify which hole fits best the incoming process. And the main advantage of this best fit algorithm is that it produces the smallest leftover. So there will be no big amounts or spaces shattered or distributed unnecessarily and without use all over the main memory. The third algorithm is the worst fit algorithm. In this case, you allocate not the smallest hole, but the largest hole. The idea here is that when you allocate the largest hole, then you have the largest possible leftover hole after accommodating the new incoming process. And this, the largest hole that remains after accommodating the new incoming process, will enable you to take more processes in future allocations at a better chance than the other best fit algorithm. In this algorithm, we also must search the entire list. This algorithm produces the largest leftover hole, and as I said, it gives you a better chance for future allocation of incoming additional processes. The first fit and the best fit are better than the worst fit in terms of speed and storage utilization. Each one has its own advantages and drawbacks. And in certain designs, depending on the type of operating system, the type of applications that the computer is supposed to be running, then you could select some algorithms and not others as to the requirement. We talked in previous slides about the holes. What happens if you have scattered holes, a large number of them, but not enough, not a single one of them is enough to accommodate a new request? In other words, you may have what is called external fragmentation, where total memory space exists to satisfy a request. However, this total is scattered and is not contiguous. It is not adjacent to each other. Another type of fragmentation could happen. The other type is called the internal fragmentation. In this case, the allocated memory may be slightly larger than the requested memory. And the difference between the allocated memory and the requested memory is memory internal to a partition but is wasted. So you have these two types of fragmentation, the external and the internal. How do we deal with the external fragmentation? We deal with the external fragmentation by compaction. We shuffle the memory contents to place all free memory together in one large block. So we combine the various scattered memory areas, we combine them together to produce one large block. This process is called compaction. Compaction is possible only if relocation is dynamic. If there is dynamic relocation procedure going on all the time, then you can do compaction. And this is done at execution time. The input-output problem, in this case that happens, is that the latch job in the memory could present a difficulty because the latch job could be involved in input-output. And one of the ways to overcome this problem is to do the input-output only into operating system buffers and not directly. Now, we said that we have certain cases arising because the processes, the spaces are not contiguous. The logical address space of a process can be non-contiguous. So what do we do in this case? This is explained by knowing that the logical address space is allocated a certain part of the physical memory whenever that part of the physical memory is available, thereby producing non-contiguous logical address space residing in the main memory physical address space mapping. What we do in this case to overcome such issue is we divide the physical memory into fixed size blocks. So now we are not dealing with the main physical memory as one large block. We are dealing with it as a large number of fixed size blocks. These fixed size blocks are called frames. Normally, the size is arranged to be a power of 2, between 512 bytes and 8,192 bytes. At the same time, we also divide the logical memory into blocks of the same size. These are called pages. So we have blocks of the same size. On one side, it is the side of the logical memory, and we call them pages. On the other side, it is the side of the main memory, and we call them frames. And we have a mechanism to keep track of all the free frames. Now, in order to run a program of size n pages, we need to find n free frames on the side of the main memory. And then we load the program. We load the n pages of the program into the n free frames of the main memory. And in order to keep track of this allocation, we have what is called a page table. The logic addresses to the logical addresses of the program represented in the pages to the physical addresses in the main memory represented in the frames. However, this may produce internal fragmentation as we explained it in the previous slide. Now, what is the scheme for this translation of addresses? To translate the logical addresses, we divide the logical address, which is, of course, generated by the CPU, into a page number segment and a page offset segment. The page number segment P is an index into a page table that contains the base address of each page in the physical memory. So the page number gives us the base address of each page in the physical memory. This table that exists and that is indexed by the page number P is used in combination with what is called a page offset D. The base address is used in combination to define the actual physical memory address that is sent to the memory unit. And you can see in front of you the division of the two parts, the page number and the page offset. For a given logical address space 2 to the power m and page size 2 to the power n, you have the page number occupying m minus n bits and the page offset occupying n bits. This is the hardware that assists in the paging procedure. You have the CPU on the left that generates the logical address, and the logical address consists of the two parts, P and D. P is a lead to a certain location in the page table, and the D is actually the offset. This location in the page table gives us the frame where we put it in the main memory. Once we obtain the frame F in the main memory, we add to it the D, which is the offset that we obtained from the logical address, and this gives us the combined total address, physical address, that points to a certain location in the main memory. On the right, in the physical main memory, you can see that F is what points to the start of the space in the main memory where we are going to start putting the logical address, and it has a length of D in the physical memory. This is a model of the logical and the physical memory paging. On the left, we have the logical memory that is generated. On the right, we have the physical main memory locations. The physical main memory locations have frame numbers, and the logical memory locations have page numbers. And in between, as you can see, we have the page table. This page table will give us which frame number in the physical memory has to accommodate which page of the logical memory. So, for example, here you have page 0 in the logical memory being placed in frame number 1 in the physical memory, the shaded area, the gray area. Similarly, for page 1, 2, and 3, let's say we consider page 3 in the logical memory. From the page table, it gives us the location in the physical memory as 7. So this is placed in frame number 7 in the physical memory. Now here we have a subdivision of memories. We have 32-byte memory and 4-byte pages. On the left, you have the logical memory with its pages. Each page has 4 bytes in it. And since a byte is 8 bits, then there are bits in that page. On the right, we have the physical memory. Again, as you can see, it consists of 4-byte frames. In the middle, you can see the page table mapping the logical memory into the physical memory. For example, you can see that the page 0, 1, 2, 3 that contain A, B, C, D in the logical memory are mapped A, C, D in number 20, which is the number 5 in the page table, because we are starting from 0. We are starting the numbering from 0. So number 5 frame will be the 6th frame in the physical memory. The same thing for the others. Let's say number 1 in the logical memory, it goes into frame number 6 in the physical memory, and frame number 6 in the physical memory is the 7th, because we are starting from 0 again, is the 7th frame. So you count 1, 2, 3, 4, 5, 6, 7, and you will see that it contains E, F, G, H, which is the content of page 1 in the logical one for the remaining pages. What about free frames? Because we are dynamically allocating the pages to frames, we are bound to get free frames. And we have to keep a track of these free frames so that we know how to use them later on. On the left, you have a new process, page 0, 1, 2, 3, and we have a free frame list, 14, 13, 18, 20, 15. These are shaded in gray in the second column of the drawing A. This is before allocation to the free frames. What happens after allocation to the free frames? We have the various pages of the new process allocated to certain frames from the free frame list. In the example drawn, page 0 is allocated to frame 14. Page 1 is allocated to frame 13. Page 2 is allocated to frame 18. Page 3 is allocated to frame 20. Allocation to the physical memory, then we are left with one free frame, which is number 15. This could remain to be allocated for any future request for a new process. Implementation of a page table. The page table, of course, has to be kept in the main memory because it is referred to. We have two registers, the page table base register, PTBR, that points to the page table itself, and the page table length register, PRLR, that gives the size of the page table. Now, in this way of access, every data or instruction access will entail two memory accesses. One for the page table and another one for the data or instruction inside the page table. This causes delay in the operation because you have to double the time because of the presence of two accesses for every data or instruction access. This problem can be solved by using a special fast lookup hardware cache called associative memory or translation look-aside buffer, TLB. With the TLB, you do not need to have two accesses for every data or instruction access, as we will see in the next slide. In certain TLBs, we store the address space identifiers, ASIDs, in each TLB entry. And this uniquely identifies each process to provide address space protection for that process. You remember in one of the previous slides, we talked about the necessity for protection. And One of the schemes that are used for protection is this address space identifier. The associative memory that we talked about in the previous slide is depicted in this slide. You have a column for the page number and a corresponding one for the frame number. If you want to do address translation of PD, then if P is in the associative register, you get the frame number out. Otherwise, you get the frame number from the page table in the main memory. This is a diagram showing this operation. You have the CPU on the left generating the logical address with its P and D segments. First, you consider the P and you look in the TLB for which frame number corresponds to this P. If you find a frame number corresponding to this P, then you consider you have a TLB hit. If you do not find a frame number corresponding to P, then you consider that you have a TLB miss. If you have a TLB hit, then this is what you use, and of course you have to hit the D, the offset, to obtain the final physical address. However, if you have a TLB miss, then you get the F number from the page table, not from the TLB, and this will be added to the D to produce the final physical address. Here we have the associative lookup being, the title of this slide is the effective access time. How to calculate the effective access time. You have the associative lookup being epsilon time unit. Let's assume that the memory cycle time is 1 microsecond. Then we have the hit ratio, which is defined as the percentage of times that a page number is found in the associative registers. So if out of 100 times you find the page number in the associative registers in 80 of these 100 times, then you get that the hit ratio is equal to 80%. Of course, this ratio is related to the number of the associative registers. It's a matter of increasing the chance of finding the page number in the associative registers. Let us designate the hit ratio by alpha. Then we can calculate the effective access time, EAT, as 1 plus epsilon in brackets multiplied by alpha plus 2 plus epsilon in brackets multiply alpha in brackets. And this boils down to 2 plus epsilon minus alpha. The memory protection is implemented by associating protection bit with each frame. You associate a valid, invalid bit to each entry in the page table, where valid indicates that the associated page is in the process logical address space and is thus a legal page. In the invalid case, if you put an invalid bit, this indicates the page not in the process logical address space. Here you have on the left the page list, page 0, 1 up to 5 in this example. Then on the right you have the mapped physical address. So you have the frames containing each page. This is given a. Then you have the page table, giving you the page number and the corresponding frame number. But in addition to that, you have another column giving you the valid, invalid bit that we said is used for protection. Shared pages. What is a shared code? One copy of the read-only code shared among processes. When you get one copy of the read-only code, the reentrant code as it is sometimes called, gets shared amongst the processes, then it is shared code. Examples are text editors, compilers, Windows systems, and so on. This shared code must appear in the same location in the logical address space of all the processes. Otherwise, it will not be shared amongst all the processes. Each process keeps a separate copy of the code and data. The pages for the private code and data can appear anywhere in the logical address space. Here you have process P1 with the edit 1, edit 2, edit 3, data 1. You have process P2, the same thing, edit 1, 2, 3, and data 2. And then process 3 with edit 1, 2, 3, data 3. Now, the page table for P1 is given 3461, which corresponds to the frame number. So you have edit 1 in frame number 3 in the main memory. You have edit 2 in frame number 4 in the main memory. You have edit 3 in frame number 6 in the main memory, and you have data 1 in frame number 1 in the main memory. Coming to process P2, the edit 1, edit 2, edit 3 have to refer to the same physical location in the main memory. So they have the same numbers, 3, 4, 6 as process 1 and as process P3. However, the data itself that is related to each separate process is not shared. So you have the data 1 in frame 1 in the physical memory, you have the data 3 in frame 2, and you have the data 2 in frame 7 in the physical memory. So only the shared code has the same physical memory location amongst the operations of the processes. Now we come to the structure of the page table. You have hierarchical paging, hashed page tables, and inverted page tables. Let us discuss each one. In the hierarchical page tables, you break up the logical address space into multiple page tables. So you have logical address space that is generated by the CPU. You break it up into more than one page table. And you connect the page table in a hierarchy. A simple technique is to have 2 levels, but it could be more. In this diagram, you have the 2-level page table scheme. On the left, you have the outer page table, and each outer page is or leads you to other page tables. So the central column gives you the page of the page table, not the actual direct location in the physical memory. These pages of the page table will guide you to the actual frame in the physical memory location. So you have an intermediate stage that is paging the page table. You don't go directly from the page table to the physical memory. You go through a transit stage, which is you page the pages, and then that paged page in the page table. We have to continue saying page table because it's in hierarchy. The name appears twice. It goes to the actual physical location. An example of 2-level paging, you have a logical address on 32-bit machine with 1K page size. You can divide it into a page number consisting of 22 bits, a page offset consisting of 10 bits. In fact, if you go back a few slides, whatever we explained regarding the page number and the page offset is clarified here in terms of bits. Since the page table is paged, the page number is divided into 12-bit page number and a 10-bit page offset. Therefore, the segmentation in a logical address is you have the page number with 12 bits giving you the page number, and then a page offset giving you 10 bits. And you have the remainder from the 22 bits minus the 12 bits, you have the remainder as a 10-bit page offset. Here, P is an index into the outer page table, and this P1 and P2 is the displacement within the page of the outer page table. Identify the outer page, then you identify the displacement within the outer page, then you identify the displacement within the inner page. And they are 12, 10, and 10. The address translation scheme here, the logical address P1, P2, and D. First, in the outer page table, you find where is P1, and then this will guide you to the page of the page table, which is the inner page table, and this is indicated by P2. Finally, this will guide you to the D, the displacement in the actual physical memory. Here, again, is the outer page, inner page, and offset. Outer page, this P1 in this example, is 42 bits. The inner page, 10 bits, and the offset is 12. This is an example of a scheme having 3 levels, not just 2 levels, because the top one is split into the bottom one. In other words, you have in the bottom one a second outer page and a first outer page and an inner page and an offset. So the 42 in the outer page is split into 32 second outer page plus 10 first outer page. That makes up 42. And then you go to the inner page, which is 10, and then to the offset, which is 12. The hashed page tables, these are common in address spaces. In this scheme, the virtual page number is hashed into a page table. This page table contains a chain of elements hashing to the same location. So you have a chain of elements, not just a single element, that hash to the same location in the memory. Virtual page numbers are compared in this chain, searching for a match. If a match is found, the corresponding physical frame is extracted. This is a diagram giving you the hashed page table. On the left, you have the logical address with its P and D segments. Then the P is subjected to a hash function that gives you its value in the hash table. Then this value is compared to each sequence in the chain. If it is not found in the first sequence, then it goes to the second. If it is not found in the second, then it goes to the third, and so on, until it finds the corresponding R. The R corresponding to P in one of the sequences. When it finds that, then it uses that in the formulation or mapping to the physical address, but of course it has to add the D to it before giving the final physical address in the physical memory. Finally, we have the inverted page table. In this case, we have one entry for each page of memory. So we go and look at it in a reverse viewpoint. We look at the physical memory arrangement and how it reflects back in reverse to our paging. The sequence of the virtual address stored in that real memory location. So again, we are concentrating to start with at the physical memory location with the information about the process that owns that page. So you have information on which process originally led to that storage in the physical memory. This scheme decreases the memory needed to store each page table, but increases the time needed to search the table when a page reference occurs. We use hash table to limit search to one or at most a few page table entries. This is the diagram for the inverted page table scheme. You have the CPU giving you the P, the process ID, with the P and the D, the usual logical address. Then you do a search on the process ID. What does it correspond to as P? This search is done in the page table. Then you go to the D and add it to the found I to give you the physical memory address. Segmentation, memory management scheme that supports user view of memory. Now, whatever we explained is a system view of the memory. What about the user view of the memory? The user view of the memory consists of how the user formulates his program code and how he segments it in his is a collection of segments. As the user, variables, local or global, common blocks, stack, symbol table, arrays, and so forth. So here is a diagram giving you the user's view of a program. For example, you have a certain subroutine, a certain symbol table, and you have the way that the user deals with them is a main program, a square root function, a stack, and This comprises the logical view giving the logical address from the user's viewpoint. Now, how do we map this logical view of segmentation from the user's viewpoint into the physical memory space? We have on the left the user space, and on the right we have the physical memory space. And for each segment we have a certain location in the physical memory. The architecture for segmentation is as follows. The logical address consists of a two-tuple, the segment number and the offset. The segment table maps the two-dimensional physical addresses, and each table entry has a base containing the starting physical address where the segments reside in memory, and a limit as before, which specifies the length of the segment. There is a segment table base register that points to the segment table's location in the physical memory. And of course, there is a corresponding segment table length register, STLR, that indicates the number of segments, the length in terms of segments used by a program. The segment number is legal, is valid if S is less than the STLR. How do protection? With each entry in the segment table, we associate a validation bit equal to 0, and this indicates an illegal segment. And we have read, write, execute privileges associated as well. The protection bits associated with the segments also are used. Code sharing occurs at the segment level. Code sharing in the memory. Since segments vary in length, the memory allocation is dynamic storage allocation. A segmentation example is shown in the next slide. This is a segmentation example. It has the CPU, then the segment part, the displacement or offset part, and then first you have to check the segment part. This will give you the limit in the segment table. Now we're talking about segments, not about pages. And the corresponding will give you the base in the physical memory. This base is added to the displacement or the offset and give you, both of the addition gives you the physical memory location. Of course, this has to be less than the limit as we explained in the previous slide. Otherwise, it will give you a trap, an addressing error. This is an example of segmentation. It gives you the logical address space and the physical memory. And for every segment on the left in the logical address, you have the limit and the base that have been explained in the previous slide, and these will guide you to the location in the physical memory. So you know exactly which segment resides in which physical memory space. Now we take a brief look at the Intel Pentium. The Intel Pentium supports both segmentation and segmentation with paging. The CPU generates the logical address. This is given to a segmentation unit that produces linear addresses. Linear in terms of a sequence of bits, as we saw earlier. The linear address that is produced is given to a paging unit. This paging unit generates a physical address in the main memory. The paging units form the equivalent of the memory management unit. This is a diagram and a linear address arrangement. At the top, you have the CPU. It gives you the logical address. This is passed on to a segmentation unit. This gives you the linear address. This is passed on to a paging unit that gives you the physical address in the physical memory. And at the bottom, you find the actual linear address. It has a P1, P2, and an offset. A P1 of 10, P2 of 10, and an offset D of 12. How do you arrange that in practice? You have the logical address with a selector and an offset. The selector will lead you to the segment descriptor. This is a descriptor table that has the segments, the segment numbers, and once you pick up the correct segment descriptor, you have to add to it the offset to give you the 32-bit linear address that we saw in the previous slide. This is the paging architecture of Pentium. You have the page directory at the higher level with the page table and the offset. So page directory followed by page table followed by the offset. This is the logical address. The page directory goes into the page directory into CR3 register, and the page table goes into a page table, and the offset goes into 4 kilobyte page. So the offset is within the allocated space. The page directory goes into a 4 megabyte page to give you the final location. If you break the linear address in Linux, you will find that it is broken into 4 parts: the global directory, the middle directory, the page table, and the offset. This is a 3-level paging scheme in Linux. The linear address at the top with the global directory, the middle directory, the page table, and the offset sections. Then the global directory goes into the global directory as a global directory entry. This will be tracked in the middle directory by the middle directory entry, which goes into the middle directory. Once you specify the middle directory entry, this is tracked to the page table with the page table entry, and finally the offset is introduced within the page frame in the memory. This is the end of chapter 8.